So let me start with a few announcements. So the assignment 3 solution is posted. Assignment 4 is now online. It's due, let me see, I feel like it's due the 5th of December. And since that's the last week of class, there will be no extensions, if you want it marked, obviously. And then the other thing is the course evaluations. So if you're at the School of Mines, please go see the administrative assistant there, Connie, and she'll give you a form to use for evaluating the course. And then at USD, please go see Mary. So I'll remind you guys by email, but it's very useful for us to have the course evaluated. So please make sure that you go see one of the administrative assistants at your campus or the campus closest to you to fill out the forms. Any questions? So I think we have 4 lectures left, right? 2 this week and 2 next week. And then I believe the exam is on a Thursday. I'll have to double check, but I'll have to make sure that no class Wednesday. Which Wednesday? Next week? Or this Wednesday? I thought there would be class this week, Wednesday. Why not?
They have no class Wednesday to give people a travel day with Thanksgiving. I mean, it's no big deal. We can I know I can plug in and listen to the lecture. I just thought I'd let you know that on the calendar they have this Wednesday as a no class day.
Okay. Yeah, no, if it's a no class day, there's no class for sure. I'll check the calendar and confirm, but I trust that you're correct. So if that is indeed the case, no class on Wednesday. I'll send an email to everybody going over about the course evaluations, and I'll make a final confirmation on that. Somebody else had heard about this no class Wednesday? To confirm, Michelle? Okay. All right. So it sounds like there's no class this Wednesday. All right. Okay, so in that case, we have 3 classes left. And if the exam is on a Thursday, I want to do a review lecture. Either I'll do the review lecture as the last class, so that'll be Wednesday the 3rd of December, or I might do a review class maybe the Monday of the exam week. So on a day where there is no class, and I'll do a review session that you're welcome to join if you want. Okay, so we'll have 1 lecture dedicated to review, whether it's still during class time or before exams. And I'll let you know. Any questions? Okay. So I start with a summary. So we've been looking at canonical transformations, and canonical transformations are ones that preserve the canonical equations in these new transformed coordinates. And the goal is to find a set of coordinates, Q and P, where the Hamiltonian is easier and the equations of motion are easier. So the idea of these canonical transformations is that we usually go from a set of Qi, little qi, and little pi to a set of big capital Qi and capital Pi. We usually go from the Hamiltonian and we change its name to K. So H is a function of the lowercase q and p, whereas K is a function of the capital Q and P. So I have a bit of a cold that I'm recovering, so I'm like coughing into the microphone a few times here. And then the whole point of the transformation being canonical is that the canonical equations are preserved, so the Hamilton's canonical equations of motion. So it's a canonical transformation. If the canonical equations are preserved. And then last time we did a bunch of things on Poisson brackets and canonical transformations. And we found an easy way to test if a transformation is canonical. Using Poisson brackets. And so if the Poisson bracket of capital Qi with capital P j is equal to delta ij, the Kronecker delta, and the Poisson bracket of capital Qi with capital Qj is equal to the Poisson bracket of capital Pi with capital Pj, which is equal to 0. So if those conditions are met, then we show that the transformation is canonical. So it's very easy, right? You'll have these equations for capital Q and capital P in terms of little q and little p, and you can easily calculate the Poisson brackets to see that whether the transformation is canonical. And the more important thing that we saw was that Poisson brackets are what's called canonical invariants. So if you have the Poisson bracket of some sort of function, capital U and capital V, evaluated in the little q and little p, that is equal to the Poisson bracket evaluated in the capital Q and capital P. So if a transformation is canonical and you evaluate the Poisson bracket of something, that Poisson bracket is equal to the same thing no matter what coordinates you use to evaluate it. And that's very powerful. So that means that the above tests of the canonical equations of when you do the Poisson bracket of the capital Q and capital P, then you can evaluate that in the little q and little p coordinates. which usually is easy since capital Q and capital P are typically given as functions of little q and little p, i.e. the transformation equations. That also means that, remember, you can use a Poisson bracket formalism to determine if things are conserved. For example, if something commutes with the Hamiltonian, if the Poisson bracket of something with the Hamiltonian is 0, that quantity is conserved. So that quantity, you can do that test in either coordinate system. And if it's conserved in one, it will be conserved in the other. Okay. Any questions about that? So I want to do a little brief thing on infinitesimal canonical transformations. So consider a canonical transformation where capital Qi is given by lowercase qi plus delta qi, and capital Pi is given by lowercase pi plus delta pi. So it's a transformation. It's a coordinate transformation, and I'm saying it's canonical, but it's an infinitesimal transformation, just like we did in previous chapters. Okay. Now remember, when we can write a transformation in terms of a generating function. And for these canonical equations, we had these generating functions which we called f. So let's say that this particular canonical transformation is given by a generating function f, right? So let's say this is given by generating function f, which I'm going to set as the sum over I of lowercase qi and capital letter pi, plus epsilon, some small number, times g, a function of the little qi and the capital pi. So that's my generating function. And so recall that first part of the generating function we showed in one of the examples that this is just the identity transformation. So my generating function really, it's the identity transformation which does basically nothing, plus epsilon g. And so the g is really the part that transforms the coordinates. Okay? And so the epsilon I'm going to say is small. Now, this is generating function of the second type. So from table 8.1, given this function, we can find what the transformation equations are. And from table 8.1, the transformation equations are given by lowercase pi is di f by di lowercase qi. And if I do di f by di qi, right, that's okay. So don't know why I got kicked out. Oh, come on. Okay. Hopefully this gets better. Okay, so just applying the generating function of the second type, the transformation equation is given by, for the little pi, di f by di qi, which gives me capital Pi plus epsilon di g by di qi. And then the other equation is that capital Qi is given by di f by di capital Pi. So that picks out the Qi, and then it's plus epsilon di g by di capital Pi. So compare that to the equations I have at the top of the screen, right? So the second equation I have here is exactly in the same form as the one that's at the top of the screen. And the first equation I can just rewrite as capital Pi is equal to lowercase pi minus epsilon di g by di qi. Okay, so if I compare the two equations I have now with the two equations at the top of the screen, I can tell what delta Qi and delta Pi should be. All right, delta Qi is epsilon di g by di capital Pi, and delta Pi is minus epsilon di g by di Qi. So we have delta Qi is equal to epsilon di g by di capital Pi, and delta lowercase pi is minus epsilon di capital G by di Qi, lowercase qi. And again, I don't know why it's so slow to update. Now I'm going to do a little trick here. Delta Qi, so that's equal to epsilon di g by di capital Pi. The capital Pi is lowercase pi plus delta Pi. And so this delta Pi here is small. So if I do the derivative of di g by di capital Pi, it is equal to di g by di little pi plus delta pi. But since delta pi is small, the derivative with respect of g with respect to capital Pi is almost equal to the derivative of g with respect to lowercase pi. And so that's almost equal to epsilon times di g by di lowercase pi. Okay, so that's the little trick here. So if I use now the notation of Poisson brackets, delta qi is equal to epsilon di g by di lowercase pi, right, which we just wrote. If I write that as a Poisson bracket, that's epsilon times the Poisson bracket of qi, little qi with capital G. Remember, when you take the Poisson bracket of qi with G, the Poisson bracket is di g by di pi. And similarly with delta pi, so delta pi is minus epsilon di g by di lowercase qi, and that's equal to epsilon of the Poisson bracket of lowercase pi with G. So we can write that the transformation equations are capital Qi is lowercase qi plus epsilon Poisson bracket of qi and g, and capital Pi is given by lowercase pi plus epsilon times the Poisson bracket of lowercase pi with g. Okay? This is just because we've enforced the canonical transformation. Now consider the case when our function g is given by the Hamiltonian. So we're going to use the Hamiltonian as part of the transformation. We're absolutely free to do that. We can take any function that we want. So if g is given by the Hamiltonian, then delta qi is given by epsilon times the Poisson bracket of qi with the Hamiltonian. And then, of course, you recall that the Poisson bracket of something with the Hamiltonian is the total time derivative of that thing. So this is the same as epsilon dqi by dt. And similarly, delta pi is given by epsilon dpi by dt. Okay, so then that particular transformation, when you take g to be the Hamiltonian, that means that the capital Qi is given by the lowercase qi plus epsilon dqi by dt, and the capital Pi is given by the lowercase pi plus epsilon dpi by dt. All right? Or in other words, qi is, capital Qi is equal to little qi evaluated at t plus epsilon. And capital Pi is given by lowercase pi evaluated at t plus epsilon. So what did we just do here? We considered a canonical transformation given by some generating function. And then for that function, that transformation to be canonical, we found that the QI's, the capital Q's and the capital P's are given by the little q's and the little p's plus epsilon times some Poisson bracket that goes with the generating function. And we chose a specific case of the generating function given by the Hamiltonian, and then we found that the canonical transformations give the variables evaluated at a later time. And so what we can conclude is that the Hamiltonian is the generating function for a transformation that advances the variables in time. Okay? Let's write it out in a sentence. So the Hamiltonian is the generating function for a transformation that takes the canonical variables forward in time. So it's again a very deep statement, right? And it's again related to quantum mechanics, where you use the Hamiltonian to find out the time development of the wave function. And it also gives us this connection again. Remember, the Hamiltonian is often the total energy. So again, this connection between energy and translation in time. So it's quite a neat result. So you can think of the Hamiltonian as the canonical transformation that advances the canonical variables in time. Okay? It's a pretty deep statement. Any questions about that? Okay, so then the next thing we're going to look at is the Hamilton-Jacobi equation. Sometimes this is called the Hamilton-Jacobi theory or the Hamilton-Jacobi method. And so remember, I had made you a promise earlier on that we would find a way that how to find out the canonical transformation where all the variables are cyclic. And so that's what the Hamilton-Jacobi equation will do. So far we've built up this whole formalism, and we understand what a canonical transformation is and the properties that it has, but we still don't know how to find the best possible canonical transformation. And that's what we're going to do now. Okay? So remember, at the beginning of the chapter, we did a derivation of the conditions for a transformation to be canonical. And we did that by comparing the Lagrangian into transformed and untransformed frames, and we forced them to be equal to each other within a time derivative. And that gave us these conditions on the generating function and on how to find the modified Hamiltonian and how to use the generating function to get the transformation equations. And we did that for generating function of the first type. And then I told you that I give you that table 8.1, which does it for all 4 types. And then I promise you that we'd do it for at least one more type. And so we'll, in the process of deriving the Hamilton-Jacobi equation, we're going to do that now for the function of the second type. So consider a canonical transformation of the second type. Given by the generating function f, and f is going to be F2, so of the second type, and F2, if it's the second type, means it depends on lowercase qi, capital case pi, and t, and then minus this term here that we need to simplify things. So it's the sum over capital Qi and capital Pi. All right. So remember, the generating function has to mix the new and old coordinates, and if it's a second type, it mixes the lowercase q's with the uppercase p's. Okay, so that's our generating function. So that means the total time derivative of this function, which we're going to need in a second, is given by the sum over I of di f2 by di lowercase qi dot, plus di f2 by di capital Pi dot, and then minus the second term's derivative, so it's the product rule, so then it's minus capital Qi, capital Pi dot, minus capital Qi dot, capital Pi, and then outside of the sum, I have in the notes I wrote this is minus di f by di t. I feel like it should be a plus. Well, let's do it with a plus, even though that's not what we have in the notes. But I think it has to be plus di f2 by di t. Oh, the excitement. Let's see if it works out. So now we want to write that the Lagrangian in the untransformed coordinates is the same as the Lagrangian in the transformed coordinates plus the total time derivative. So the Lagrangian in the untransformed coordinates, this is what we did back in equation 8.4 in the notes. So the Lagrangian in the untransformed coordinates is the sum over I of lowercase qi dot pi minus the Hamiltonian. And that's got to equal on the right-hand side in the transformed coordinates the sum over I, or the capital Qi dot pi minus the transformed Hamiltonian capital K, and then plus the total time derivative of f. So then it's plus what we just had, the sum over I of di f2 by di lowercase qi dot, plus di f2 by di capital Pi dot, minus capital Qi Pi dot, minus capital Qi dot Pi, and then outside of the sum, plus di f2 by di t. Okay, so now you can see, we added in this extra term minus the sum Qi Pi inside of f, because that's going to cancel the first term on the right-hand side of the equation. And what I'm going to do, I'm going to group on the left-hand side the terms that go with Qi dot, and on the left-hand side, I'm going to, on the left, the terms with lowercase qi dot, and on the right-hand side, terms with the capital PI dot. So that gives me on the left-hand side, we have the sum over I of lowercase pi minus di f2 by di lowercase qi times qi dot. And that's going to be equal minus h. I guess we'll keep the h on this side. And that's equal to the sum over I of di f2 by di capital PI, so factoring the terms in PI dot, minus capital QI times capital PI dot, and then plus di f2 by di t. So now we enforce this equation to be true, and that gives us the conditions for a canonical equation, right? For a canonical transformation. So forcing this to be true, that means we can say that the lowercase pi is given by the di f2 by di lowercase qi. So if we force these two equations to be, this equation to be true, we can do so by forcing that the sums are equal to 0. So that gives us the conditions on the pi, the lowercase pi, and the capital case qi. And so the capital case qi must be given by di f2 by di capital pi. Note that these are exactly the transformations equations we used earlier when we did our thing on the Hamiltonian and the time transformations. And then that means that, well, it looks like I forgot a k here, didn't I? In the equation. Hasn't refreshed yet. There should be a k at the end, or where we want to put it. And so then we find that k is given by the Hamiltonian plus di f2 by di t. So that's good. The sign did work out, and there was a mistake in the notes in the derivation part. Okay. So now all we've done so far is we've just considered a canonical transformation of the second type, and we derived the conditions for the transformation to be canonical given a generating function. All right, so this is exactly what we did at the beginning of the chapter. So we're going to do a small change of notation. And instead of F2, we're going to call it capital S. All right, so we're just going to rename our generating function from F2 to S. And the reason we do that is because we'll see in a minute that S actually ends up being the action. Okay. Now, the genius part is here, is we can choose any S that we like. Since the above equations guarantee that the transformation will be canonical. Okay. So let's choose S such that K is equal to 0. It's perfectly legal. So we're going to make that specific choice of generating functions so that the Hamiltonian in the transformed coordinates is identically 0. And so that's exactly what we're after, right? If the Hamiltonian is 0, then all the coordinates are cyclic, because clearly none of them appear in the Hamiltonian. So what we find is that this gives us the condition to find S, that generating function, which we can then use. So imposing that K equals 0, right, so K equals 0, and K means that H plus di S by di T is equal to 0. And so that's actually the Hamilton-Jacobi equation. So we should be, this is going to get very confusing now because we have all sorts of variables in here. Some of them are constants because they're cyclic, and some of them aren't. So we should be a little bit careful to write out what everything depends on. So H is a function of the lowercase qi, the lowercase pi, and t. Okay? Now, the lowercase pi, if we look at our transformation equations above, the lowercase pi are given by di F2 by di Qi, but F2 we call S. So the lowercase pi are given by di S by di Qi. Okay? So we want to write H, and we want to point out that H is a function of lowercase qi. It's a function of di S by di lowercase qi and t. Now S you recall is a function of the lowercase qi and the capital Pi and t. But capital Pi are equal to constants, right? Because all in the transformed Hamiltonian, all the Q's and P's are constant, right? Because capital Qi dot is equal to di K by di Qi, but di K is by di Ki is 0. So capital Qi dot and capital Pi dot are equal to 0. And so Qi and Pi, capital Qi and capital Pi are constants, right? So S depends on lowercase qi, but capital case P is a constant in T. So we're going to call these constants, the capital Pi's, we're going to call alpha i's. So we're going to call alpha and beta things that are constant. Okay. So because k equals 0, qi dot equals 0, and pi dot equals 0, capital Q, capital P. And so those two are constants, and what we're going to call them is we're going to call the pi's, the capital Pi's, we're going to call alpha i's, and the capital Qi's we're going to call beta i's. Now also note from our transformation equations, right, the capital Qi is di s by di capital Pi, and so that's di s by di alpha I. So the conclusion here is that beta I are given by di s by di alpha I. So if we write the Hamilton-Jacobi equation again, we can write it as it's the Hamiltonian, which depends on Qi, and it's di by di Qi of s, and s depends on Qi, and then the capital Pi, which we've called alpha I, and t. And the Hamiltonian also potentially depends on t, plus the partial derivative di by di t of s. I'm just going to write s again, s Qi alpha I and t, and that's equal to 0. Where alpha i's are equal to constants, and beta i's can be obtained as di s by di alpha I. And so that's the way we write the Hamilton-Jacobi equation. So it's a partial differential equation for s. So what you do is you write the Hamiltonian, and every time you have a Qi, you leave it as it is. But every time you have a lowercase pi, you replace that lowercase pi by di by di Qi of s. And then you have this di by di t of s at the end equals 0. And that's a partial differential equation in s. For s, sorry. So in principle, if you could solve this partial differential equation, you can find that canonical transformation for which the transform Hamiltonian is identically 0, and for which all the coordinates are cyclic. So before we do an example, let's look at the connection to the action. Remember I said we would call it S instead of F2 because it's related to the action. So S is a function of lowercase qi, alpha I, and t. So that means that the total time derivative of s, ds by dt, is equal to the sum over I of di s by di qi dot. Now there's no di s by di alpha I because alpha I dot is 0. All right, so I don't need that term. And then plus di s by di t. And if I use the transformation equation, lowercase pi is given by di s by di lowercase qi. The transformed Hamiltonian k is given by our initial Hamiltonian H plus di S by di T. And that's got to be equal to 0. Now if we go back and look at our ds by dt equation, note that the di S by di Qi is actually Pi, right? I just wrote it there. So ds by dt is the sum over I of Pi Qi dot. Now, the di S by di T is equal to minus H, right? From this equation here. So the ds by dt is the sum of Pi Qi dot minus di S by dt, or plus di S by dt, which is equal to minus H. And so, of course, you recognize that as the Lagrangian. And so S is actually equal to the integral of L dt plus some constant. And so S actually is equal to the action, at least within some additive constant. Let's consider one more little thing about the Hamilton-Jacobi equation. If H does not depend on time, then H is a constant. That's, I guess, a little bit redundant thing to say. And let's call that constant capital E. It might not necessarily be the energy, right, depending on what H depends on. The constant might be just the Jacobi integral, but not necessarily equal to T plus V. Okay. So if I look at the Hamilton-Jacobi equation, let's call it the HJ equation. We have the function H, which depends on lowercase qi di S by di lowercase qi and T, plus di S by di T. And that's got to equal to 0. Now, we can try a solution for S that's given by a function W that only depends on Qi and alpha I. Remember, S is a function of Qi, alpha I, and T. So I want to separate out the T dependence from S. So let's try a solution for S where S is given by some function W of Qi and alpha I minus ET. And if I put that into Hamilton-Jacobi equation, right, I get that H, which doesn't depend on time, so it's H depends on Qi and di W by di Qi plus di S by di T. In S, I've put in the T dependence with the E term, as I'm going to move it to the other side, and I'm just going to say it's equal to E. So that's a partial differential equation for the function W of Qi and alpha I. And so now, okay, I've just done a bunch of mathematical manipulations, and it's not super obvious what just happened. But maybe you can think of another situation where you have an equation that kind of looks like this, where you have Hamiltonian something equal energy something, maybe. All right, that's the equation that you have in quantum mechanics. The Hamiltonian times the wave function is energy times the wave function. So this is the mathematical equivalent of that. The Hamiltonian on the one side equals energy on the other side. And it's a partial differential equation for this function W. So this is exactly analogous to quantum mechanics. So that's pretty neat. And so in classical mechanics, this is a partial differential equation for the function W. And in quantum mechanics, it's the Schrodinger equation, which is a partial differential equation for the wave function. Okay? So I have a little part at the end of this chapter on the connection to quantum mechanics. But the Hamilton-Jacobi equation actually is very, very similar to the Schrodinger equation. So let's finish today's lecture with an example. So it's all very mathematical, right? The goal here is to get you to see this deeper connection between symmetries and conservation laws, as well as the deeper connection between classical mechanics and quantum mechanics. So that quantum mechanics isn't just some absurd thing pulled out of thin air. It really does follow through from classical mechanics. But that being said, that means there aren't that many examples that you can do that are easy to solve analytically. So we'll do again now. We've done the simple harmonic oscillator with the canonical transformation, and now we'll do it with the Hamilton-Jacobi equation. So this is example 8.5 in the notes. We're going to solve the simple harmonic oscillator using Hamilton-Jacobi theory. Okay? So let's start by the Hamiltonian for a simple harmonic oscillator. The Hamiltonian is given by p squared over 2m plus k over 2 q squared. And so in this case, it's the t plus v, so kinetic energy in terms of the momentum is p squared over 2m, and the potential energy is a half kx squared, and we're calling them p and q. Okay? So we want to write this. I guess I forgot to mention a terminology. The function S is called Hamilton's principal function. So the action, and technically the action differs from S by additive constant, but we call this function S that gives us the transformation equation, we call that Hamilton's principal function. And then in the case where the Hamiltonian doesn't depend on time, what we just did, and we can use this W instead of S, we call that the Hamilton's characteristic function. Okay, so S is Hamilton's principal function, and W is Hamilton's characteristic function. Okay. So let's write the Hamilton-Jacobi equation. So the Hamilton-Jacobi equation is that, so the HJ equation is that the Hamiltonian as a function of Qi, well, let's not use the i's, let's just say Q. So the Hamiltonian given as Q di S by di Q and T plus di S by di T equals 0. That's just the Hamilton-Jacobi equation. So let's plug that in using what we know for the Hamiltonian, right? So let me plug in, let me write now the Hamiltonian that we have into the Hamilton-Jacobi equation. So the Hamiltonian as a function of Q di S by di Q and T is 1 over 2m P squared, but now P squared is di S by di Q squared plus a half K Q squared plus di S by di T. All right, so I've written the Hamiltonian where I've replaced the P by di S by di Q. So now I have, as promised, a partial differential equation for S. Right, S depends in this case on little q and t, and this is the partial differential equation that it satisfies. If I can solve for S, then I will know the transformation where the transformed Hamiltonian is identically 0. Okay? So let's go ahead and solve this. Now, note that the Hamiltonian does not depend explicitly on time. Thus, I can separate it out. So this S of Qi alpha I, well, let me just say, let's say Qi alpha I and T. What we just saw, that we can write this as W. No, actually, I'm not going to put the Qi, so it's just confusing. So this function S, which depends on Q, alpha, and T, can be written as a function W that depends only on Q and alpha, minus alpha T. And so I'm saying that alpha here is equal to the energy. Okay? So I can put that back into the Hamilton-Jacobi equation. So if I put that into the Hamilton-Jacobi equation, I have 1 over 2m. Now, di S by di Q, the only part of S that depends on Q is W. So I can write that as di W by di Q. So that's square, so that's still the P term, plus a half K Q squared, and that's going to be equal to alpha. So alpha equals the total energy in this case. Now, this equation, I only have derivatives with respect to Q. So at this point, it doesn't necessarily, there's no distinction between the partial derivative of W with respect to Q compared to the total derivative of W with respect to Q, because W only depends on Q, so the partial derivative is the total derivative. So if I write this as a total derivative, I have 1 over 2m times dW by dQ all squared plus k over 2q squared equals alpha. So that's now an ordinary differential equation for W, and it's separable. So I can write this as dW by dQ equals 2m alpha minus mk q squared, and it's all square rooted. All right, let me also write, introduce omega as the square root of k over m. So k is omega squared m. And I can now write this, I can just integrate this equation, right? So I have W is equal to the integral of the square root of 2m alpha minus, now I'm going to replace the mk using the omega. So it's m times omega squared m, so that's m squared omega squared q squared. All right, that's an integral that you can do. And so our function s now is minus alpha t plus this integral, 2m alpha minus m squared omega squared squared. All right, so we found our generating function. And that's some integral that's, you know, mostly trivial to do. So we've already noticed that alpha, our constant of motion, is energy. And we know that there must be a second constant of motion. Because now all the variables in the transformed version are cyclic, right? So then the beta I, which is given by di-s by di-alpha, are also constant. So that constant beta, if I now do di-s by di-alpha, the first term is minus t, and then the second term, so I can bring the di by di-alpha inside of the integral, right? And if you do that partial derivative, you get 2m over the square root of 2m alpha minus m squared omega squared q squared dq. At this point, I'm going to integrate it. You'll just look it up. So beta is equal to minus t. And if you do that integral, you'll find that it's equal to 1 over omega. It's arc sine, so inverse sine of q times the square root of m omega squared over 2 alpha. So beta is a constant, alpha is a constant, and this gives us an equation for beta. So you can now invert this equation to get Q, right? So if you multiply both sides by omega, and then you bring the t to the other side, and then you do an arc sign, or arc sign. So then you end up with Q times that square root is equal to omega times beta plus t. So we can invert this. And you get that Q of t is that square root, but 1 over that square root, because I moved to the other side, sine of omega times beta plus t. And so then we actually solved the problem there. We actually found what the function Q of t was, where alpha and beta are constants that you can solve using the initial conditions. So it's a little bit hard to wrap your mind around how this works, but you saw here an example of applying the Hamilton-Jacobi equation to a problem. So that we took the simple harmonic oscillator, we wrote the Hamilton-Jacobi equation. That was a partial differential equation for S. Then we noticed that S was separable into a W and an independent time-dependent term. And then we found the constants of the motion, alpha and beta, right, which are basically Qi and Pi, capital Qi and capital Pi. And then we transform back to get lowercase q, and then we can get lowercase p. Oh, looks like I need to have one more page. Lowercase p, if we want pi of t, that's got to be di s by di q. I just don't need to put an I. And so if I take di s by di q, that's di by di q of the function s, which was minus alpha t plus the integral of square root of 2m alpha minus m squared omega squared q squared dq. And that apparently is equal to square root of 2m alpha minus m squared omega squared q squared. And then if you substitute in the value that we had for q, that's square root of 2m alpha times the square root of 1 minus sine squared of omega times beta plus t. And 1 minus sine squared is cos squared. So the square root of that is cos. And we end up with 2m alpha times cos of omega times beta plus t. So our problem is solved, and this is the result that you expect, right? If the Q goes as sine, then P has to go as cos, because you remember for a simple harmonic oscillator in phase space, you trace out circles or ellipses. The alpha is the total energy, and that's equal to the capital Pi. So this transformation, this canonical transformation that solves this, takes the lowercase pi to the total energy, and then the Qi to these betas, which are physically difficult to interpret. And so that's it for today. So any questions about that? Yeah, so go over the notes again. That's actually a lot of material that we did today. But it's sort of a really neat part of classical mechanics. So I'll remind you, assignment 4 is posted, and it's due next Friday, I guess. There's no extensions, because I need to be able to mark it before the exams. And I'll do a review session, whether that's the week of the exam or the last week of class. I haven't decided yet. I guess it depends how far we get. So if there's no more questions, everybody have a very nice Thanksgiving. And I'll talk to you all next Monday. So no class on Wednesday. Thanks, everyone.